So today we'll discuss this concept of uniform pressure and uniform wear in friction of pivot bearing. Okay, actually, uh, we can write the design of pivot bearing. The design of pivot bearings is based on the following assumptions. Assumptions. What are the first assumption is distribution of pressure distribution of pressure, or you can say intensity of pressure is uniform all around the bearing surface. And second assumption is the wear is uniform. The wear is uniform throughout throughout the contact, that means the bearing bearing surfaces. Now, based on these aforementioned assumptions, based on these aforementioned assumptions, two theories have been proposed. Two theories have been proposed for pivot and collar bearings for calculating the total frictional torque involved. And the first one is uniform pressure theory. Pressure theory. Now, what is this? If the bearings are new, if the bearings are new and the fitting, or you can say the fit between the between the shaft and bearing surface bearing surface is perfect, is perfect, it is safe, it is safe to assume that the load is well distributed over the entire area of contact entire area of contact. In other words, you can say, in other words, the intensity of pressure distributed over the area of contact is constant is constant, or you can say P is constant, okay, for uniform pressure theory. So it is clear that this theory we can use in case the bearing is new and it is assumed that the fitting between the shaft and bearing surface is perfect. Okay, in that case you will be using uniform pressure theory. Now second one is uniform wear theory. Uniform wear theory. Now when bearing become old, the bearing surface will be worn out. The wear wear of the surface at different point of contact at different point of contact depend upon the product of intensity of pressure, intensity of pressure and velocity of rubbing. Okay, now the velocity of rubbing is also different as it depends upon the radii from the axis of rotation. Axis of rotation for a given uniform angular speed of shaft. Speed of shaft. Okay, so we know that rubbing velocity, this rubbing velocity V is equal to R dot omega. Okay, so as I told you, this wear is proportional to the product of intensity of pressure and rubbing velocity. So we can say it is also proportional to the product of P into R. So for uniform wear theory, we can say P dot R should be constant. Okay. P is the intensity of pressure acting at the contact surface. R is the radius of rotation from the shaft axis. Okay. Let's say we have this shaft. Okay, for a flat pivot, if we're saying, okay, we're just discussing one example. This is the shaft axis, and this one is the bearing. Okay, flat bearing, flat pivot bearing, you can say. Now, uh, we know that the radii of rotation, if you consider different sections, let's say if I am considering this section, okay, so the radii of rotation will be 1, let's say it is R1 here. Likewise, at a different section somewhere here, it will be, let's say it is R2. So it is varying because the distance from the axis of rotation is increasing. So, but at every instant, this P dot R should be constant. Okay. So, if R is going on increasing, we have to reduce the intensity of pressure in order to keep PR as a constant value. Okay. Another example you can take. Suppose I am writing with a chalk. Okay, and I choose that the stroke width, let's say it is like this. Okay, if it is older, and if I'm choosing a new chalk, okay, so with a new chalk, it will be much more thinner. Okay, but as the chalk worn out, and if I'm applying the same pressure, then the thickness will increase. So in order to have the same stroke width, okay, what I will do, as the chalk get older, I will apply uh, less intensity of pressure while writing, so that I can have the same thickness. So it is same principle is applied here in the uniform wear theory. Will decrease the intensity of pressure as the worn out increases. Okay, in order to keep your PR a constant. Okay, so this is the fact. Now, let's say we can write, in other words, in other words, as we go away from the axis of shaft, axis of rotation, you can say, that is R. increases and the intensity of pressure is to be decreased so as to keep this PR, okay, PR as a constant. Okay, the frictional torque determined by uniform pressure theory. Uniform pressure theory is more than the torque calculated by uniform wear theory. Wear theory. So for safe design of bearings, the uniform pressure theory should be used since it will give us maximum power that lost in overcoming friction friction so that net available power is minimum for safe design. Okay, now we have to derive this equation based on uniform pressure theory and uniform wear theory for pivot, conical pivot and truncated conical pivot. So first we'll consider flat pivot. Okay, flat pivot. So if I draw the schematic, let me change the color. Uh, the arrangement is somewhat like this. We have a shaft here. Okay. Then the load acting in the shaft is, let's say, W, and this is the pivot area. Okay, pivot area. Change the color here. I am not drawing the whole pivot, just marking this area. Okay, this is the pivot area. So this part is shaft, this one is pivot. Now the central axis of rotation is here. Okay, and let's say r is the shaft radius. This is the shaft radius. Now if you draw the top view, it will be somewhat like this. Okay, let's say so the radius is r. Okay, you can see now in this. Let us take a small ring. Okay, for our derivation, small ring of thickness, this hashed portion. Okay, at a distance, at a radius, suppose r1, and the radius and the thickness of the ring is, let's say, dr1. Okay, now let's say that let w is the total load over the bearing surface, over the bearing surface. P, small p, is the intensity of pressure. R is the radius of shaft, or you can say radius of pivot, either radius of pivot. Mu is the coefficient of friction. Okay, now as I told you, consider an elemental ring of radius r1 and thickness del r1. Okay, now first we'll consider the case of uniform pressure. Okay, so considering uniform pressure, area of the elemental ring, I can write area of elemental ring will be 2 pi r1 into del r1. Okay, now the load on the ring is equal to pressure multiplied with area, isn't it? So let's say it is del W. So del W is intensity of pressure is P into area is 2 pi R1 into del R1. Okay. Now we know that total load on the ring W will be equal to integration 0 to R. Okay. 2p pi R1 del R1. Okay. So your W will be, take this out, 2 pi p, okay, take it out. So we have r1 square by 2, okay, from 0 to r, okay. So it will be equal to pi p r square, okay. So you can say intensity of pressure P will be W by pi r square. This is the intensity of pressure. Okay. Now this way you can calculate. Now the frictional resistance. Okay. Frictional resistance on the elemental ring. Frictional resistance on the elemental ring. Elemental ring. Let's say it is del Fr. Okay. Frictional force is equal to the coefficient of friction mu into the load acting on the rib, del W. Okay, so it will be equal to mu 2 pi r1 del r1 into your pressure, area into pressure is your load. Okay, now the frictional torque will be how much then? Frictional torque acting on the ring, acting on the ring uh, will be, let's say it is T, okay, denoted by T. So R, it is del Fr multiplied with the radius R1. So it will be mu, okay, 2 pi P R1 square, okay, R1 square into uh, d R1. Okay, now the total frictional torque, total frictional torque, T will be the integration 0 to r mu 2 pi p 2 pi p r1 square, okay, dr1. So you take this out, 2 pi p mu, take it out, so you'll have r1 cube by 3, okay, from 0 to r. So it will be 2 pi p mu, okay, r3 cube by 3, or you can say this T is equal to 2 by 3 pi mu p r cube. I think I'm clear to all of you. Okay. Now, if you substitute the value of P, okay, from this equation, let's say this is 1 and this is 2. So if you can write here that substituting the value of P from equation 1, this T will be equal to uh, 2 by 3 pi mu. So instead of this P, we can write down W by pi r square, okay, into r cube. So this T can be represented as 2 by 3 mu W R. Okay, so this is the total frictional torque if you are considering uniform pressure. Okay, let's say this is equation 3. Now the power loss in friction P will be T dot omega. Okay, so this P will be 2 by 3 mu W R into omega. Okay, so the unit you should remember that it should be in Newton meter and it should be in watt. So and omega should be in radian per second, which is 2 pi n by 60. And if you are taking this as kilo Newton meter, this will be kilowatt. Okay, power. Unit you have to be very careful. Okay. Now considering uniform wear. Considering uniform wear, for uniform wear, we have this P dot R is equal to constant, we know, as I told you. Okay, P dot R is constant. So for the ring element, if you consider, it will be P R dot R1 is equal to constant, or we can say that P is equal to C by R1. Okay, intensity of pressure is C by R1. Let's say this is equation 1. So the load taken by the ring, okay, load taken by the ring del W is P into area of the ring. So I can write P into 2 pi R1 d R1, and instead of P I'll substitute C by R1 into 2 pi R1 d R1. Okay, so this is equal to basically 2 pi C d R1. Okay, let's say this is equation 2, the load taken by the ring. Now what will be the total load? Total load taken, W, will be integration from 0 to R. Okay, 2 pi C d R1. So it will be 2 pi C R. Okay, 2 pi C R. Now the constant C will be W by 2 pi R. This will be the value of constant we got. Let's say this is equation 3. Now the frictional torque on the ring ring element is given by given by T for the ring element TR. So mu del W R1. Okay. So this mu into del W is 2 pi C dr1, okay, into R1. So it is 2 pi mu, can write 2 pi mu CR1 dr1. Okay. Now the total frictional torque, total frictional torque T will be from 0 to R 2 pi mu CR1 dr1. So take this out, 2 pi mu C, okay, so it will be R square by 2. Okay. Now substituting the value of C, let's say this is equation how much 4. Okay. This is the total frictional torque. Now substituting the value of C in equation 4, this total frictional torque T will be 2 pi mu, and what is C here? It is W by 2 pi R. So W by 2 pi R into R square by 2. Okay. So this will give us this T is equal to half mu W R. Let's say this is equation 5. And the power lost in friction will be same. Power lost in friction P will be T dot omega. Okay, and units will be same as previous case, where this omega is 2 pi n by 60 radian per second. Okay, now next is for conical bearing, conical pivot, sorry, conical pivot, conical pivot. So for conical pivot, let's say the schematic is somewhere like this. We have this shaft, this is the shaft axis, and the pivot area is, let's say, this much, this part. Okay, now let's say the total angle is, as I told you, cone angle is 2 alpha. Okay, now we'll choose, we'll draw the top view. Okay, let's say the top view is, sorry, let's say this is the top view, a circle. Okay, and we'll choose one element here, ring element. Okay, the total radius is R, and the elemental ring is at the radius R1 and is having thickness dr1. Okay, so we can write here, let this alpha is the semi cone angle. Okay, as alpha is the cone angle, 2 alpha is the cone angle, so this alpha is the semicone angle. R is the radius of shaft. Okay, R is the radius of shaft. Radius of shaft, or can say radius of pivot. Then mu is the coefficient of friction between shaft and bearing. Shaft and bearing. And P is the normal pressure intensity. Normal pressure intensity. Then del Wn is the normal load acting on the ring that is equal to pressure into area of the elemental ring. Area of the elemental ring. Okay, now we know that from the geometry of the figure, you can say if we choose on the front view, this is the elemental ring. Okay, and the length of this elemental ring is suppose it is dl. Okay, so this dl is basically dr1 by sin alpha. Okay, dl is equal to dr1 by sin alpha. So from the geometry of the figure, we can say from the geometry this dl is equal to dr1 by sin alpha. Now area of the elemental ring, area of the elemental ring is 2 pi r1 into del L. Okay, or you can say 2 pi r1 into del r1 by sin alpha. Okay, now considering uniform pressure, considering uniform pressure load on the element ring, load on the elemental ring del Wn is 2 pi p r1 del r1 by sin alpha. So vertical component of this load del W is del Wn, that is normal load dot sin alpha. Okay, so this del W, you can say it is 2 pi p r1 dr1. Okay, so total vertical load on the bearing this W will be basically integration of 0 to r 2 pi p r1 d r1. So take this out, 2 pi p will have r1 square by 2 from 0 to r. Okay, so which is equal to 2 pi p r square by 2, that is pi p r square. Okay, or you can say that intensity of pressure P is equal to W by pi r square. And then frictional torque on the ring, let's say this is Fr is equal to mu Wn, mu del Wn, so it is mu 2 pi p r1 del r1 by sin alpha. Okay, so the frictional torque on the ring, this is the frictional force. So frictional torque will be frictional torque on the ring Tr will be your frictional force on the ring multiplied with the radius r1. So this will be mu 2 pi p r1 square, okay, del r1 by sin alpha. So the total frictional torque T is given by integration 0 to r. So mu 2 pi p r1 square, okay, del r1 by sin alpha. So take this out, 2 pi mu p by sin alpha and here it will be R1Q divided by 302R. Okay, so this T can be represented as your 2 by 3 mu W R by sin alpha if you are substituting the value of P. Okay, from here substituting the value of P, or you can say this T is equal to 2 by 3 mu W R cosec alpha. Okay, this is for uniform pressure. Now for uniform wear and power loss will be same. Power lost in friction P will be T dot omega. Now considering uniform wear, this we know that P1 R1 is equal to constant, where C is a constant. Okay, and the load taken by the ring, load taken by the ring del W is equal to pressure into area. So this is P1 into 2 pi R1 dR1. Okay, or you can say that C into 2 pi into dR1, substituting the value of P1 R1 here. Now the total load taken by the bearing W will be 0 to R 2 pi C dR1. Okay, so take this out, 2 pi C, so it will be R. Okay, 2 pi CR. Now the frictional torque, and here you can say that C is equal to W by 2 pi R, value of constant. Okay, so the frictional torque on the ring TR is equal to mu del W into R1 by sin alpha, or you can say mu 2 pi C R1 by sin alpha into dR1, and the total frictional torque is given by And this T will be integration of 0 to R for mu 2 pi CR1 CR1 cosec alpha dr1, or we can say 2 pi mu c cosec alpha r1 square by 2 from 0 to r. Okay, so this t will be equal to pi mu c cosec alpha r square. Okay, now you substitute the value of c, so this t will be pi mu w by 2 pi r cosec alpha r square. Okay, or we can say it will be half mu w r cosec alpha. Okay, considering uniform wear. And the power lost in friction, power lost in friction P is equal to d omega. So likewise, your assignment is to derive to find out total frictional torque and power for truncated conical, or you can say trapezoidal uh, pivot bearing. Okay, so you have to solve this and show it to me.